Welcome back. Good news. If you survived video number 3, that was the most difficult video to get through. We introduced a lot of concepts and hypothesis testing that are going to keep appearing again and again and again. So in this video, we're going to shift to a different type of data. We're going to consider numeric data. And if we have one sample of numeric data, something we might do is test the population mean. As a reminder, I'm assuming that you've watched the previous videos, so you're familiar with setting up hypotheses and choosing a significance level. We'll now go through steps 3 through 7 for testing a mean. Okay, so consider the following problem. An auto manufacturer advertises that a certain model of their car has a fuel efficiency of 32 miles per gallon on highway. A consumer group is concerned that the efficiency might actually be lower than advertised. We'll see the data in a moment, but we want to know, is there convincing evidence at the 5% significance level that this model of car actually does indeed have a lower gas mileage than is being advertised? Okay, so you know the drill. Based on the situation at hand, figure out what parameter we should test and write a set of hypotheses. And we've been given the 5% significance level, so I've got that written down already. So pause the video and you can check your answer in a moment. All right, so our data here is numeric. We're measuring the fuel efficiency and coming up with a number to represent, how far the car can go per gallon. And the claim or the worry by this consumer group is that the efficiency is lower than advertised. So that's a kind of difference in a single direction. We think that the true mean fuel efficiency might be less than 32. Our null hypothesis we know has to have the equal sign in it, but the stuff on both sides, the mu and the 32, will be the same. All right. And in this situation, mu is a population mean, specifically the mean highway fuel efficiency among all cars of this certain model. And we're not told what it is. Is it a Honda Accord or a Toyota Highlander? We don't know, but all cars of that type. All right, so step 3 we know is that we are going to need to check certain things to see if our test will work in this situation. And when we're testing a single mean, we're going to be using a t-test, okay? So if it was categorical data, we did a z-test. If it's numeric data, we do a t-test. So in order to do this t-test and use this t-test statistic, we need a few things, just like we needed in our z-test for proportion. We'll talk about degrees of freedom in a minute, but the premise is the same, that if the null hypothesis were true, we can create a theoretical distribution based on this formula, and then we can compare our observed result to that theoretical distribution to see if it lines up pretty well or if it doesn't. So the conditions for the one sample t-test, you may remember because you hopefully saw them when you did a one sample t confidence interval. At the basic level, they're also the same conditions as the z-test for proportion. That is, we need normality, we need independence, and we need a random sample. The details of how we check normality are going to be a little different, though. So if we're testing the population mean, we're going to use the sample mean to help achieve that. So it's that sample mean which must have an approximately normal distribution. So a couple ways that might happen. If our sample size is large, and we'll consider large to be at least 30 members in our sample, then we can simply apply the central limit theorem, which you hopefully saw in Stat 1. This, in a nutshell, says that sample means are approximately normal when a sample size is large. Okay, so if our sample size is at least 30, we get a free pass for normality. If our sample size is less than 30, we're not necessarily stuck, but we're going to have to plot the data and see, what shape does our sample distribution have. So you could make a histogram maybe, or a box plot. There's a few other ways. but we want to assess to see, does it seem to be a fairly bell-shaped distribution? We would not want to see any strong skew or outliers. If those are present, we would need to stop. This test does not work if there's skew or outliers and the sample size is small. Okay, next we need independence. So this will be assessed using the same criteria as in the z-test. If sampling is without replacement, we need to verify that no more than 10% of the population was included in the sample. And then third, just like with the z-test, where we need to have some reassurance that our sample was randomly selected from the population, which is going to cause it to be representative and unbiased. Okay, so here's our data. And I've got a histogram down below, a box plot above it, and something called a normal quantile plot above that. All right, so is it reasonable that our sample mean, x bar, has a normal distribution? Well, our sample size is only 8 measurements. So it's not large enough to apply the central limit theorem. So we'll instead consult the graph of our data and see, based on this sample distribution, does it seem plausible that the population might have a normal distribution? I would say yes. We see that our histogram is symmetric with a peak in the middle and tapers off same amount on both sides. If we consult our box plot, we see that the whiskers are more or less the same length. The two sides of the box are pretty close in width, and we don't have any outliers. So based on our sample looking pretty normal, it's not too much of a stretch to assume that the population values are normally distributed. So as a result, the sample mean would be as well. It is still an assumption because we don't have the complete picture. We're still basing this off of only 8 measurements. All right. Next, for independence, one benefit of a small sample size is that you're probably not going to approach 10% of the population size. So take your n and multiply by 10. So as long as there's at least 80 cars of this type, then we're okay on independence. All right. Lastly, it did say in the problem that we have 8 randomly selected cars of this model type. So we know that the sample is random. In this case, we don't have to assume. Okay, next, in step 4, we compute our test statistic. So we select this formula based on the fact that we're dealing with numeric data. We can find the sample mean and the sample standard deviation using whatever methods you like. Maybe that's a calculator shortcut, or maybe that's the long way by hand. So those would go in the formula. And again, the general idea is the same as with the z-statistic. On top, we're going to compare our sample statistic to the hypothesized value. So that is, in the sample, yeah, it does seem like the cars actually got a little bit worse gas mileage than 32 miles per gallon. But is that a significant difference? Well, it all depends on how much do we expect x bar to vary from sample to sample due to sampling variability. So on the bottom here, we have the standard error of the mean. That's going to describe, typically how much do we expect x bar to fluctuate. Okay, so we crunch those numbers and we wind up with a t statistic of negative 2.76. All right, with the t distribution, we have this funny thing called degrees of freedom. No time in this video. We'll talk more about this in stat 2, but just be aware that for this test, our degrees of freedom is going to be the sample size minus 1. So 8 cars minus 1 leaves 7 degrees of freedom. All right, so you hopefully saw t distributions when you did confidence intervals. So this dashed line here represents the standard normal, or z distribution. So notice it's bell-shaped, it's centered at 0. It's also the tallest of all these distributions. The other distributions in the different colors are t distributions. And each t distribution is defined by its degrees of freedom. So we said that for this test, 8 cars minus 1 left 7 degrees of freedom. So 7 doesn't happen to be pictured, but it's going to be awfully close to this green line for 8. All right, so you'll notice that this t-distribution is a lot like the z-distribution. It's not that far away, but it is a little bit less tall in the center and a little bit thicker out in the tails. The green is above the dashed line out here and on the left as well. Okay. So this is our theoretical distribution, or close to it, and that's what we're going to use as the basis for comparison for our t-statistic that we previously calculated. So where does negative 2.76 fall on that curve? All right, so if it's negative, we're going to be on the left-hand side. Negative 2.76 is probably somewhere about here. All right. And then recall, we need to find our p-value. So this is a probability, using area under the curve, and specifically area in the direction as specified by the alternative hypothesis. So here we have a little arrowhead pointing to the left. So our p-value is going to be the area under the t-distribution with 7 degrees of freedom. That's to the left of negative 2.76. So this piece out here. There's a calculator function that can find area under the t-distribution. It's called TCDF. And working from left to right, we need a lower boundary, an upper boundary, and it needs to know the degrees of freedom. So here, I want a very large negative number to represent negative infinity. And then I'm going to accumulate area up until I reach negative 2.76. And that's on this curve with 7 degrees of freedom. Okay, so under the roughly the green curve, although it's 7 degrees of freedom, not 8, this portion is a little over 1% of the whole thing. So that's our p-value, 0.014. Once you've got your p-value, pretty much any hypothesis test is the same. We're going to use the same decision rule as we did in the previous video. So remember, the rule is if the p-value is less than or equal to alpha, we can reject the null hypothesis. So that's what happens here. 0.014 is indeed less than 0.05. So we can reject the null hypothesis and conclude that the alternative hypothesis is true. Right. Finally, bring it all together. Remember, this problem was about cars, and was there evidence that the fuel efficiency is actually less than advertised? Yes, we found strong enough evidence at the 5% significance level that this type of car does indeed have a mean highway fuel efficiency that is less than 32 miles per gallon. Okay, so we're quite certain that that's the case, that that's the truth. But just a little bit of review here. Remember from video 2, most tests are correct in their conclusion, but sometimes they make an error. So consider for a moment, if an error did occur, what type of error would it have been? Would it have been a type 1 or a type 2? If you guessed a type 1, you are correct. So that is, we rejected the null hypothesis. So the type of error where we failed to reject the null hypothesis could not have occurred. So it's definitely not a type 2, and that leaves a type 1 that might have occurred. All right, so that's it for video number 4. Video number 5 is just a couple practice problems, nothing new, but just sort of practice tying everything together.